Welcome to the Abstract Synthesis Podcast, where we share the stories behind remarkable academic papers in the world of program synthesis. Brought to you by AGI Research Lab and DIA, I'll be your host, Brian Landers. And our guest today is the intrepid Andrew Cropper. He's an associate professor at the University of Helsinki and a principal investigator at Ellis Institute, Finland. He previously led an AI research group at the University of Oxford and earned his PhD at Imperial College London. His fascinating work is all about combining logical reasoning and machine learning and focuses on inductive logic programming, ILP, which involves learning symbolic rules or logic programs from data. And he and his research group are responsible for developing the very cool ILP system Popper, which we'll talk about later. Andrew, welcome to the show.
Thank you for inviting me.
It's great to have you. In today's episode, in every episode, we focus on one paper just to kind of anchor the conversation and not go too far, not sprawl too far afield. But today's paper that we'll be focusing on is Inductive Logic Programming at 30, a new introduction, which was published in 2022 in the Journal of Artificial Intelligence Research. So Andrew, this paper is a beast. It covers a lot of ground. I'm only partially regretful I picked this one for our topic today because there's just so darn much to explore, but let's do our best. And the paper commemorates 30 years since the inception of ILP and gives us a comprehensive modern introduction to the field. I'm a bit new to academia, so what is this type of paper called? Is it like a review paper or an opinion paper? What do you call it?
So this is a weird paper in that often you have survey papers are very common, where people will review the last, say, 5 or 10 years of the literature, or even shorter time frames. They are very common. But this is kind of an overview of the whole field, of even going back to the 90s and covering some of those topics. So we weren't actually sure, or we couldn't find any similar papers. So I'd say it's a survey paper, but of the whole field.
It's amazing. And how long does it take to write a paper like this? Because it feels so extensive in the research and citing alone, let alone like your new contributions and ideas must have taken a long time.
Yeah, this paper took a long time. A long time. I think it was at least 2 years, not obviously working on it every day, but from the inception to submission of the second version, because it went through some revisions, it was about 2.5 years, maybe. I think we started working in 2019 and it was published in 2022. So yeah, a lot of time, a lot of effort. It was a beast. Yeah.
Congratulations. That is a really remarkable effort and definitely paid off. It's a wonderful paper.
One of the most remarkable things, which I should point out, are the reviewers. Because it's not an easy paper to review. And I can't remember if we had 3 reviewers, but one of them, their review itself was about 15 pages. So honestly, it was exceptional reviewing. They went through it all. They gave good constructive feedback. They spotted out. It was remarkable. I've never seen a review that long. So yeah, the reviewers need a lot of acknowledgement, really do in this case, because that was a beast to review. Yeah.
Shout out to the reviewers. They don't get a lot of love often, for papers, but it's super important part of the process. And just making sure everything's correct. It's hard to get everything, factually correct and dates and things. So that's really cool. Nice shout out. I appreciate that. What sparked why now? Why was now the right time and the motivation to write this reflection on ILP?
The only selfish reasons. I did my PhD. Then I started my own research group and I had all students come, we really want to do ILP. What should we read? So I could give them this big, thick, dense book from, 1994 or 98 or something. Or I could give them the original kind of introductory paper of ILP from 91. Otherwise, was it? There was another book from 2008, but again, it was a big, thick book. There was nothing that you could just give to a student and say, look, here's a paper, you can skim through it, find the most important parts without giving them a big daunting book. So that was the reason. I wanted a paper we could say, look, if you want to work on ILP, look at this paper. Purely selfish reasons. Yeah.
No, it worked out great because for anyone else, introduction into the field, that's wonderful resource. Makes total sense. Thank you for doing it in the first place. What I have a question, kind of background wise for you. You've spent so much of your career working on inductive logic programming. How did you discover this? Like, where did you start getting interested in this field?
I have a slightly unusual background in that I did my undergraduate degree, then I worked in industry, then I did a master's degree, then I worked in industry. And after my master's degree, I worked as a research engineer in a startup. And I was just doing machine learning, normal things. And I was just bored. I was so bored. I'm a computer scientist. Like, I'm not a statistician. I like algorithms. I like, proving correctness, understanding complexity. I really like computer science. And then most machine learning, statistical machine learning, it's computer science, but actually small statistics. I just wasn't enjoying it. Also, is all the big deal about big data. So you'd run something for hours and wait. Oh, there was a mistake. Run it again. I just found it completely unrewarding. That was it. It was just I wasn't enjoying it. Like I said, algorithms, proving things, coming up with new algorithms. It's fun. So then I just happened to see a PhD advert at Imperial College London by Stephen Muggleton. I had never heard of, like almost everyone else, I had never heard of ILP before. I had no idea what it was about. Like, even the words, like inductive, that's a bit weird for some people. Logic programming, that's, I think I'd never really, I kind of heard of it, but I didn't know logic very well. But it just sounded interesting. I had a call with Stephen, and he just seemed very enthusiastic. So I left the company, started a PhD at Imperium. Yeah, it's kind of impromptu, really. Yeah.
It's amazing. Are you glad you made that choice? I would guess so, because you work so much.
I'm so glad. Yeah, I'm so glad. It sounds really cheesy. I just love what I do. It's fun. It's really fun. You can actually do something new, contribute, reason about it. I just really enjoy what I'm doing.
It shows, and you've contributed so much to this niche of AI. So I think that everyone's better off for you having, stumbled upon it and really committed. Hey, before we dive too much into the paper, can you tell us about your co-author? This is Sebastian Dumancic. Did I say that right?
I'm entirely sure. Sebastian. Yeah. I think you have two pronunciations depending on whether you pronounce it correct or not. I say Seb. Seb started his PhD, I think he started either the same year as me or maybe 1 year later in Leuven, or KU Leuven in Belgium, which is very much prominent for ILP. Like, there's a few hubs in the world. Imperial, for instance, it's a place in Japan. And KU Leuven is one of the major hubs for not just ILP, but also declarative programming, things like that. And so he did a PhD there. And it turned out we'd met actually many years ago, but we didn't really talk. But then we met in a conference in Ichigai 2019. And he did his PhD on ILP, and his PhD was interesting. He was trying to essentially take ideas from neural networks and just copy them. He was the paper which we connected over was the idea of autoencoders. In neural networks. And we were like, what does an autoencoder, this is him. What does an autoencoder look like in a logic program? Well, it's kind of compressing a logic program by discovering these auxiliary facts. So you take your input data, can we compress it?
Yep.
I was like, that's such a cool idea. So that's anyway, we got talking. Then from that, we ended up just collaborating on quite a few papers now, just from that one meeting at the conference. And he's now in TU Delft. Assistant professor, I think. And he now have a little bit of ILP, but more, I checked with him before this to make sure I was right, more neurosymbolic. Program synthesis, neurosymbolic. Yeah. Not so much on the ILP part, but still interested in ILP.
Yeah. Definitely something we're exploring on this podcast and at Endia for ideas we look at. I love the neurosymbolic crew. They're so obsessed with the cognitive science kind of part of, how does the human brain work and how does that sort of apply to machine learning and vice versa. So definitely everyone stick around for future episodes where we talk to folks in that field. I guess let's dive in. I mean, we're talking about ILP. How do you describe it to someone totally new to this space?
Do it in a presentation. I would just put it on slides to say, look, ILP takes input examples, training examples, labeled examples. And it takes also as input background knowledge. You can just think of them as features. That's all they really are. Take these as input, and the output is a hypothesis that explains the examples given the features. Then I always make the explanation that we don't say model, which is typically used because it has a very particular meaning in logic. So it's confusing. So we use kind of what Tom Mitchell's. Have you read Tom Mitchell's machine learning book at all?
No.
It's so disappointing. It's like the best book for machine learning. He gives an overview of the whole of machine learning. Oh, it's brilliant. Anyway, he uses the term hypothesis. So you're searching the hypothesis space. And I say, that's it. If you think of it like that, it's the same as any form of supervised machine learning. I've got some examples. I want to come up with a hypothesis for them. The only difference is that rather than using, say, a statistical, coming up with a statistical hypothesis or statistical model, you come up with a set of rules, logical rules. That's the only difference. It's just the representation language you use for the output, and typically the input too, but mainly the use of logic to represent the hypothesis. That's, to me, the key feature of ILP. You could use, I don't care what you use in the middle, you could use a neural network, you could use brute force search, but as long as the output is a logic program, set of logical rules, that's what I think ILP is.
That's actually more broad than I realized in terms of, like ILP doesn't have to remain sort of on the symbolic side. That's really cool. You can use other things as tools along the way, as long as it ends up as a logic program, you're saying.
Yeah. So the good example would be, so we use, typically ILPs use Prolog, for instance. Quite a lot of algorithms are being written in Prolog, which is a logic programming language. But one of the most prominent ILP systems from ages ago was actually written in C. It was just mimicking. It was like had a Prolog interpreter inside. And then our work, it doesn't use Prolog really. It uses these declarative solvers, ASP solvers. You can think of them as SAT solvers. But then I've got a good friend, Richard Evans, who is at DeepMind, and he used neural networks to perform the search. So you can use whatever you want. So as the output is a logic program, logical rules. I think that's what ILP is.
And you mentioned Stephen Muggleton was one of the pioneers. Are there anyone else sort of, part of the legacy of ILP?
There's loads of people, like, you can trace ILP really far back to the 60s, to people who came up. So Gordon Plotkin is the one who's mentioned of it. Gordon Plotkin, more of a logician, coming up with the idea of generalization, and you have maybe two logical atoms, and you want to find the least general generalization. Anyway, things to look at that. But really, I always consider the stuff I refer back to was some work by Edward Shapiro, who, it's a shame he's not that well known, but he did a beautiful thesis where really it was the first, well, maybe this is incorrect, but one of the first real ILP systems. And it was to do with algorithmic program debugging. So the idea was that you have an algorithm and it should work on some examples, and you get an example in, and your algorithm doesn't quite work for the example. We need to revise our algorithm. So it's really program revision, but it was using learning logic programs. And I think even in the paper, he calls it, in his thesis, I think he calls it program synthesis. But most of the key ideas from ILP go back to his thesis. So say, Edward Shapiro is maybe a starting point. But then Stephen Muggleton was the one who he's at Imperial College London. He kind of brought the field together, gave it its name, and then, I don't think it's any understatement, basically dominated the field for the rest. Did most of the systems, most of the work, published most of the papers. So it's really his field, I'd say. Yeah.
Till you got there, right?
Yeah. And then there's many other people. Yeah. I'm not going to mention them all, but yeah, lots of other people. But I think those two are I always look back at Shapiro's work. Even now, I always end up loading up his thesis to just check things.
That's wonderful. I'll definitely link some of his work in the show notes so people can go, check out some of that.
Oh, it's a great thesis.
Great thesis. Yeah. You just called it out, but I mean, the topic of this show is program synthesis. ILP induces programs. It seems squarely in that sort of, area of AI. Would you agree that it is program synthesis?
It's always tricky what constitutes a program. I used to think I knew, but now I'm not entirely sure. So I don't have a good answer, because I used to, before talking to many people, I always had the idea a computer program basically had to be Turing complete, like to be a real computer program, loops, blah, blah, blah. But then some people there's a fragment of logic programs called data log programs, for instance. It's a bit technical, but they always terminate. So they don't have the Turing expressivity,
Right.
but they're called data log programs. So
Yes.
that is a program, according to people. So how do I see now?
Is this related to like temporal logic? It's also like whether programs end or not, I guess, is a area of study entirely.
Yeah, so then it gets really blurry because, for instance, is a decision tree a program? You execute it symbolically.
Yeah, sure.
So but then in decision tree induction, is that program synthesis? Yes, the lines get very blurry.
It's true. Yeah, this is cool. And there's sort of formal space of program synthesis, like formal verification and all these kinds of things, which had real world application with like chip design and things like that. So I feel like that's squarely in program synthesis. But you're right. It's good to kind of question these umbrella terms that kind of cover whole areas of study. And from somebody who's so expert at this space, that's a really notable thing to call out. So
for the most part, in ILP, you induce typically a prologue program. So that's a logic programming language, which is just inherently a program. Prologue is Turing complete. You can do anything you could do in any other language. So most systems learn Prolog programs. So yeah, we cannot not be program synthesis. It's like by definition, program synthesis. Yeah.
Right. Yep. This makes sense. We're talking about, syntax for ILP, and you mentioned Prolog, Datalog, answer set programming like ASP. Has there been any kind of consensus in the sort of ILP world as to like the best sort of, language or substrate for ILP?
No, I don't think it's no is the answer. And my immediate thought, without really thinking, is that it's not possible. In the same way you can't say there's a best programming language. In general, you can't say C is better than C++, better than Python, because they have different purposes. So for instance, just as a simple example, there are many problems which you can represent as propositional. Are you familiar with propositional logic?
Really? Can you explain more?
So propositional logic is just, all you have is a set of symbols, and they're true or false. You have no quantifiers. So you can have a rule just for symbols, they're true or false, no quantifiers at all. And actually for many applications, you can get away with that. And essentially, to get a bit technical, decision trees have the expressive power of a propositional logic. So you can take a decision tree and translate it to propositional logic. So essentially, if all you need is the same power as a decision tree, you don't need anything more. So that's fine. Often you need something else. So an example I give people is, if you want to do anything with arithmetic, so the thing with propositional logic is that you need to have a symbol to represent everything in the domain. That's rather tricky if you're working with integers. You have a lot of them.
Yeah.
So you can't do it. Yeah, that's why decision trees don't have that full expressive power, because they can't represent just natural numbers. Whereas with a first order logic or Prolog or answer set program, you can actually do this. You have quantifiers, you can represent arithmetic. So you get more power, and that means you can often express things more compactly, but then your language becomes trickier to reason about. And then in some cases you need negation, and then negation really adds a whole world of confusion. So yeah, you make the language more and more expressive, and then obviously the search becomes harder. So yeah, the short answer is there is no single best programming language. or representation language, as far as I'm aware.
So someone studying, diving into, studying ILP, they can kind of pick and choose, whatever's best for their particular use case.
Yeah, and the syntax is the same, essentially. So Prolog syntax is basically the same as something called Datalog syntax, which is basically the same as answer set programming. Answer set programming just has some extra syntax sugar, but they're all essentially the same, and they're all just first-order logic. So if you know first-order logic, you know these programming languages. That's what's great. That's a selling
Very
point
cool.
for logic programs. Yeah, if you know logic, you know how to write logic programs.
Yeah, I definitely recommend folks check it out. I think ASP looks pretty interesting too. As you said, there's some kind of sugar on top that's kind of interesting.
Yeah, it's just great. It's so nice to work with because you don't have to think. you don't have to worry about whether it's going to terminate because it always terminates. You're not going to have to worry about how you order things or the way you put the rules. You just write what you want and it does it for you. Oh, it's wonderful. I love it.
So the answer is ASP. No, I'm just kidding. I'm teasing. So, why ILP? There's a whole section in the paper about this. Really interesting to contrast with, other ML approaches. So, ML traditionally relies on, statistical inference. And by contrast, ILP relies on logical inference, and uses techniques like this automated reasoning and knowledge representation. I'll show here, it's in post-production, the table from the paper where it kind of compares ML and ILP. And you actually gave a shout out to our co-founder, Francois Cholet. The point was many forms of ML are notorious for their inability to generalize from small numbers of training examples, notably deep learning. So what makes ILP special here? What are some advantages it has as compared to deep learning?
But usually I kind of sell it as all the problems you have typically with deep learning or statistical machine learning, you don't have in ILP. So for instance, the clear one is interpretability. We're learning rules. There's no other way. We have a rule. You can look at it. You can teach almost anyone logic within half an hour. Actually just have to understand the rules. Not maybe the full understanding how the program works, but you can understand the syntax of a logic program in half an hour. That's such a nice feature. So instead of trying send all this research trying to understand what's going on within a neural network, for instance, we don't need to. We have it. So that's such a big selling point. But what's nice is that you can actually sidetrack. What's really nice is I could say to an ILP system, here's some data, learn some rules, show it to the user, and they'll be like, actually, I don't like that rule. That rule's wrong. Let me tell the system it's wrong because of this. And the system, because it's reasoning symbolically, can take that into account and it would obey what you've said. Even when I'm using an LM, for instance, it gives me an answer and I'm like, don't give me that answer again. It gives me the answer again. I'm like, no, do not want that answer. I've got a very funny one when I'm telling it, do not do this. I tried every way to get it to not give me the same answer and it gave me the same answer. Anyway, because we're working with a symbolic thing, we can literally say, it is not possible for you to give this again. The system's like, let's not do that again. So interpretability and the ability to reason formally about a program is a huge selling point. But then that leads on to the ability to actually just verify what's going on. I can actually reason about the logic program, use a cassette solver to make sure it works, make sure it doesn't work. I can reason about the algorithm that produced it, just check that it correctly produces it. So just this ability to do formal reasoning about what it's learning is a byproduct of this interpretability and symbolic representation. So those are two really key parts.
Wonderful.
Yeah, and then just in general, the ability to generalize. So LLMs are getting pretty good at this now compared to the old deep learning ones. So what I'm saying that in the next 1 minute is out of date, but it used to be a huge problem for neural networks just to generalize, especially with program synthesis. So there are some, it's going to sound bad, but there's some ridiculous papers where they're trying to learn, say, sorting algorithms. And they're like, look, they're trying to learn sorting algorithm. We trained it on numbers lists with at most 10 elements in the list. We gave it, 300 million examples. I said exaggeration, 300,000 examples.
Okay.
And it like performs to like 96% accuracy. And then once it goes to 11 elements on the list, it just tailed off. And then what's the point? Like, how is that? Yeah. So you don't have that with ILP because you learn a computer program. If I learn sorting, I don't learn sorting for like 1 hour, 10 elements, 11 elements. I learn a sorting algorithm. So do you see, and that's being Ein Shapiro. Pretty sure he learned sorting algorithms in his work in 1980 or so. It's not hard in syntax. So the ability to generalize is a key part of IFB from small amounts of data. So truly generalized and from small amounts of data.
The small amounts of data is very interesting. I mean, at NDIA, our goal is to, work with the ARC AGI benchmark, and that's it. It's just incredibly limited, examples of input-output pairs. But that does seem like a really huge kind of selling point of ILP is like, you don't need to train it on the entirety of all human knowledge, text content, right? You can get 3 to whatever examples of something and then be able to create these logic programs and generalize from there. Is that accurate, would you say?
Yeah, it's always caveats about that. So for instance, we can't learn a sorting algorithm from small amounts of data if we do not allow the system to learn a recursive algorithm. So the idea of recursion is that you essentially have a program or a rule in a program that calls itself. Without that, the program will not generalize. So you need certain features in order to correctly generalize. Recursion is one of the most notable ones. Essentially, imagine writing any kind of important algorithm without a loop. It's not really possible to write a good program in that case.
Yeah, for sure. And that's just like a required feature to kind of, make use of ILP, it seems like. That's actually really interesting.
Yeah, recursion is crucial. There's some tricks you can kind of get some good generalization ability without it, but in general, you need recursion for lots of concepts. Arc is a good one. You want to draw a line. Well, there's a dot, and then there's a line to the right side, to the right, and you want to keep looping until, you hit the boundary or something.
Yes.
You want recursion.
100% agree. I don't know if this may be too challenging to do without visuals, and I'm not looking for you to repeat any talks that are on YouTube or anything, but like, I guess from a high level view, can we share just how ILP works? Like, for instance, this kind of learning setting and the representational language. Is there a way that you kind of frame this that sort of works to kind of share to new people in the field?
Very simple. It's just search. So you have some examples as input, some background knowledge. And then the thing we talk about, you have something called language bias or an inductive bias. This basically says, what is a valid. Let's just keep it simple that we're only learning single rules. That just makes it quite simple. I'm looking for a rule that explains the examples given the background knowledge. The user has to say what's a valid rule. Like if I'm trying to learn a sorting algorithm, I don't want it to try to classify, to learn about the chemical structure of a drug. It's not going to help. So they have to like limit the search space. So the user has this bias. And then after that, all you're doing is searching the space of all the possible rules you could construct. So it's just a pure search problem. You could literally just say, well, I'm actually just going to consider. So the class of cases that you start with no rule whatsoever. Or you say a rule that just says everything is true. So all the examples are true. It's the simplest thing. You try it on the examples, say, maybe I have the counter examples. Some things are true when they shouldn't be. Oh, so that means our rule is essentially too general. It says everything is true. I need to make the rule, change it, typically by adding something on it. So all this is, well, out of the things I could add, what should I add? Oh, maybe I add this extra literal, this extra part. You can think of it as an extra function. Oh, we tried it now, we made it a little bit better. Maybe we excluded some of those negatives. But now there's a positive we missed. Maybe we should backtrack and try something else. So essentially, it's just pure search. There's the same as any real search algorithm. That's how I explain it. There's not much, no mystery to it. Just search.
That's a wonderful thing. I think it's nice when things, it's not that it's a simple process, but it's a simple concept that, can be made into like something powerful. You mentioned their inductive bias. Can you explain more about that? Like what is inductive bias?
Inductive bias is anything that influences search, really. So that could
Okay.
be essentially, it's just saying what can appear in a rule or not. So you might, if you're learning sorting algorithm, like I said, you want it to maybe have the functions like append or the length of a list. So you just have to tell the system that you can use these,
Oh, I see.
but
Okay.
don't use, for instance, the chemical structure of penicillin. That's not useful. It's just like it's just a bias. It's just the inductive bias. Well, the language bias just defines really the hypothesis space, the space you're searching.
I see. That's very important then. Yeah.
Yeah, and then you can also you have to specify whether you want certain features, like if you want to allow the system to have recursion, or often you need to restrict the size of a rule because there's infinitely many rules. So just imagine you're trying to synthesize computer programs. There's infinitely many computer programs. So you maybe have to say, look, only computer programs of a certain size. Yeah, that's all that inductive bias is.
So it's all about constraints.
Yeah, all
Got
forms
it.
of machine learning have them. It's not an
Huh.
IOP term. Yeah, that's why
Oh,
people
okay.
should look at Tom Mitchell's machine learning book. It's excellent because it goes through all the different neural networks, decision tree learners, support vector machines, I think, Bayes learning, and just says what the inductive bias is for each one. It's an excellent book. Great book.
All right, you heard it here, folks. Andrew recommends this book. We'll link it in the show notes. We need to get like an Amazon affiliate link for you or something.
It's actually available for free on the Tom Mitchell's website. Yeah.
Oh, that's so cool. I love it when knowledge is shared like that. That's really special. All right, we'll definitely link it then. Well, you attempted not only just defining how it works, but you went deeper in the paper around building an ILP system. There's a part of that search method, how to search the hypothesis, as you called it, space. And there are some things I've seen before. This kind of bottom up, top down. Can you give general overview of search methods?
Yeah. So, as I said, when you're searching just a hypothesis space. So again, just keep it simple. That the hypothesis space just has rules. So essentially, you're searching for the best rule. That's what we're searching for, according to some kind of cost function or loss function. So it could be, for instance, the number of examples which are covered, or the number of examples plus the size. So you assume some kind of cost function or loss function. So you have this big search space. And how they structure them is something they typically structure the search space based on the generality of the rules. Oh no, here's a good example. So perhaps I'm trying to learn whether you're happy or not. I could come up with the rule, you're happy because you live in America. Or you could be, you're happy because you live in America and you work for India, is it? How you pronounce it?
Yeah.
India. Yeah.
Like end ideas.
Yeah. So because you live in America rule is much, much more general than you live in America and you
100%.
work for India.
That's
so
right.
you structure the space based on this kind of generality of the rules. And essentially, there's two options. You could say, well, I'm first going to consider the most general possible rule. Everyone's happy. Or I could consider a really, really specific rule. It'd be like, you're happy because you work in India, and this morning for breakfast you had cheese on toast with kippers or something weird like that.
Yeah.
Both are essentially valid ways to search the space, because typically for that second case of starting at the bottom, you just look at the examples. You say, look, I know I can explain this example by saying this memorization, this example is true. That's perfectly fine. And then try to generalize from that bit. Whereas top-down just says everything is true or everything is false, and then tries to generalize. So those are the two classical ways. And people try to bridge the two, and they do fancy things where they search at the top, but then bound the search by the bottom.
Yes.
So that's the way to structure the search space and like finding a way through. Within that, there's so many different algorithms about actually how you navigate the search space. What search algorithm you use, like A* or something like that. And then also how you define the actions in the pathfinding problem. Like, how do I decide which step to take and which action to take through a rule to make it more general or more specific? So that's the classical ILP approach. The third approach, which is kind of developed recently, It's a terrible name, and we still can't come up with a good name. We call it meta-level approach.
Yes.
Maybe I should just explain that beforehand, people would just wrote the algorithm. So someone would sit, I'm going to write an algorithm, I'm going to write how it chooses which rule to do, how to revise this rule. A new approach has come called meta-level. Again, a terrible name. And it's the way you describe it, the way I try to describe it, I'm just going to be lazy. I'm going to delegate this search problem to a stat solver or an ASP solver or some form of declarative search solver and say, look, I don't care how you search the space. I have no interest.
Yeah.
Just search it. So that's what we work on, and quite a lot, another group at Imperial work on that. So we just say, look, I'm not writing my own search algorithm. I'm just going to let the very smart people in stat solvers or ASP solvers, they're really good at search, let them do it.
Yes.
That's how the new thing. And that's really nice. The selling point of that is that we don't have to maintain a search algorithm. And it makes it very, very easy to innovate and come up with new ideas. Because you can everything's declarative. So you can got a quick idea, you just write a simple rule and add it to the stat solver, the ASP solver, and it just reasons about that new rule. So it basically means our work is so much easier by this third approach, meta-level learning. Yeah.
Love it. Doesn't sounds smart if the results are great, right? It's like tool use essentially,
Yeah, precisely. And the stat solvers, I say stat solvers, but I also mean ASP solvers. They're essentially not the same thing, but in our case, we treat them as the same thing. They're incredible nowadays. They're so fast.
Agree.
We try to explain to people are very familiar with like the revolution in deep learning or statistical learning, but there's also been a revolution in stat solvers and SMT solvers in the last 15 years or so. They're so good, like amazingly good. Things that should not be solvable are solvable pretty easily.
It is magical. Yeah.
Yeah, it's magic. It's really magic.
This can seem like that. And this is what this podcast is about, just shining a light on those kind of less visible sort of areas of AI. Some cool things about like features, like kind of standout features of ILP. One I would point out would be predicate invention. So like, these logic rules, like you're mentioning, like, I'm happy and I'm in the US. Now I could take those two concepts and bundle them up into like a new kind of rule, essentially, that like represents both of those things, and then add that to kind of like a learning library or something and apply it to future things, which can allow me to generalize in a very elegant, like more concise way. And you can just keep doing that until it's useful, or, during search. And that's called lifelong learning, right? Am I saying any of this right?
Yeah, there's kind of two distinct topics. Predicate invention is distinct from lifelong learning, and you don't need to do predicate invention to do lifelong learning. Well, again, it depends on what you mean by predicate invention. It's a bit tricky, because if you're learning a new concept, that itself is a new predicate in some sense, because you're defining something new. But yeah,
I'm just laughing because it seems like in a lot of fields, like someone's like, well, what does predicate mean? What does invention mean?
Oh, yeah.
It's like, okay.
Yeah, even as we said, that the notion of computer program, I used to think I knew.
Yeah.
And now I actually,
I
try not to even talk about it because I don't know. But predicate invention, it's just getting a system to invent a new predicate, a new relation, essentially a new idea that the user didn't tell. The boring example we use, but it gets the idea across, is learning the notion of parent. So suppose you're trying to learn the notion of great-grandparent.
Mm-hmm.
Well, how do you define, like, what's a rule for great-grandparent? It's like your great-parent is the mum of your mum, or the mum of your dad, or the dad of your mum, etc., etc.
Yes. Yeah. It's a bunch of steps.
Now do it for great-great-grandparent. If for great-great-great-grandparent, you need lots and lots of rules. You have this exponentially many rules.
Exponential. Mm-hmm. Yeah.
But if you could just invent the notion of parent. So the notion of parent is you're someone's parent if you're their mum or their dad. Now the notion of great-grandparent is the parent of a parent.
Same concept, just another level. Yeah.
Yeah. But you've essentially invented this auxiliary reusable concept that makes the whole thing much, much easier to learn.
It's very
predicate
cool.
invention is essentially getting the system to come up with new symbols that better represent the data, essentially. And that's a case of trying to learn predicate invention to make something smaller. But there are often many concepts where you need predicate invention to learn something. So quicksort, like imagine trying to learn quicksort without the partition. It's rather difficult. Yeah, so there's lots of things, lots of cases where the way you could describe it, imagine writing a computer program with only one function.
Oof.
Like writing one big massive function. It's really hard.
Terrible. Yeah. And terrible code, right?
Terrible code. In some cases, depending on the programming language, but at least with logic programs, you need predicate invention to learn concepts and even to learn efficient concepts. Like you can actually reduce the complexity, the running time complexity by inventing concepts. So predicate invention is actually crucial. So it's really important for arc, like bring vector arc. If you're going from, say, learning from raw pixels, you probably want to invent the concept for like a line,
shape, right?
Yeah,
square.
Exactly.
Yep.
Yeah. So it's really crucial. So Stuart Russell has a book called, I should have looked it up first. I think it's called Human Compatible in like 2019. He might not think it now, but at the time he said he thought predicate invention was the most important concept to get good AI, getting systems that discover new knowledge.
Yeah.
That's kind of important. Yeah.
It's kind of compelling. And it certainly seems like something humans do very, very naturally as part of our, the way we understand concepts. Maybe to the detriment of our, incorrect biases from time to time. We learn them a little too aggressively, it seems like.
Almost everything we do, like just the notion of a shape, of a square. We've created the concept of a square.
Yeah.
Essentially any word we use, we're inventing a relation. So
totally.
We do it all the time. And there's many cases, I can't remember off the top of my head, but in science where you have to discover this new concept that no one had even thought about before.
That's really cool to hear about, this standout feature. And there are other ones, and people should read the paper to dive more into really cool features of ILP. There's a case studies section of the paper that talks about, I'm going to say these wrong, Aleph, tilde. Can you say them for me?
Aleph. Aleph is the first one. Tilde is the second one. Aspal
Thank you.
is the third. I think the fourth was Metagol. Yeah.
Yes. Yep. So I think, we'll let folks explore the paper and follow links from there to go explore those. But we can't get through this interview without talking about your incredible creation, which is Popper. I guess, when did you start working on Popper and what prompted you to kind of, begin actively working on it?
We started working on it during COVID. Well, the initial idea came from, I was actually visiting Josh Tenenbaum's lab in MIT, and I was speaking to Kevin Ellis, and I remember I was on board, we were talking about, I can't remember what we were talking about, but we were talking about maybe a search problem. I was just thinking, it's so stupid what we do in ILP, where we do all this search. Oh, it didn't work, let's backtrack, it didn't work. All this like failures, you don't really learn from it. And it was just like blindingly obvious that we're just wasting like 99%. If you're doing a search problem, you fail, and then you just happen to get lucky and find the right solution. But we should be learning from the failures. So that kind of idea came from there. And then with my PhD student in Oxford, we just found a way to actually encode this like idea of getting a system that really just tries to fail, learns from all its failures. And then so we did that in around, I think it was 2020. It was during COVID period. Yeah. But maybe the background was that it's really inspired by Karl Popper, the philosopher of science.
Not much about Karl Popper.
So Karl Popper, I'm going to butcher this because I'm not a philosopher, but he essentially said that there's no such thing as induction, like learning general rules from data. It's not a good way to accumulate knowledge because there's always going to be a counterexample. You can never really say what you've learned is true or false. Like it's just not a good way to accumulate knowledge. The only way you can really accumulate knowledge is by ruling things out. that's the only way, like, we can show that something is not true. It's gone.
Scientific method.
Completely, essentially, Popper was a big advocate for the notion of falsifiability. Something has to be falsifiable. And by falsifying things, by showing something's wrong, is how science advances, not by finding something that fits the data. So it's a good example of gravity. Newton had his theory about gravity, which works. And then Einstein could show, actually, Newton's wrong. It's like, not showing that Einstein is right, but that Newton is wrong. There's a case where it doesn't work.
Yep.
So we've now updated our knowledge kind of by showing that Einstein's right so far, but that Newton is wrong. So we know that's wrong. At least we think Einstein's right, but we're not really sure. It could still be proved wrong. So it's like that's the idea of Column. And then we try to use that with the ILP system. And the idea is that instead of trying to find a hypothesis that fits the data, we're trying to rule out hypotheses. That's our goal, get rid of them. If there's something left at the end, we return it to the user. But really, we're just trying to eliminate hypotheses. That's the whole idea of Popper. Searching to rule things out.
Yeah, it's beautiful. It's quite the insight you had, and then a very elegant kind of implementation of that.
Really easy. It's like one of the simplest ILP algorithms. Oh yeah, really
seems
simple.
So brilliant. But that doesn't necessarily mean it's not a wonderfully like elegant and powerful idea. Sometimes the best ideas kind of arrive like that, and they go, "Oh yeah, of course this should have existed."
Yeah, nearly all the best ideas.
That's kind of the initial inspiration of Popper, but it's grown into much more, and there are more contributors, and it's probably in use in some places. What has Popper grown into today? What does it look like nowadays?
Getting faster. It's getting much, much faster. So we've made incredible progress. Essentially, every paper we release now gets the learning time down from from over an hour for a task to a few seconds. So we're still making huge progress. And that allows us to scale to much, much bigger hypothesis spaces. So I feel like we're still in the infancy where we already have more ideas that we know what to do than we've done before. So there's still lots of potential.
Wow.
It's grown into quite a powerful system. Quite a few groups are using it. I can't remember all the different applications, but people around the world are using it. Not as many as any form of deep learning, for instance. But for ILP, it's relatively successful.
How does that feel? I mean, just knowing that you created something in the world that's, out there and people are finding value in it and they want you to keep, building upon what you've built already.
Nice that people use it. It's annoying that people find bugs because then you have to fix it. Yeah. It's like if it grew much bigger, for instance, you'd be overwhelmed by it. So it's nice to keep it small.
Yes, for sure.
But it's nice
you said you wanted to learn from failure. This was the whole core concept of Popper. It's a meta thing.
No, it's pretty good. I just like it because it's so easy to, not in terms of its power, it's so easy to try a new idea. So as a good example, we have a paper which is half accepted. And it's essentially the idea of learning where not to search before searching. So the idea in general of machine learning, you have your features, your examples. Okay, let's go search. We were like, okay, maybe we don't even look at the examples. Let's just look at the features, the background knowledge. And we find some patterns in the background knowledge that says that a certain rule in the hypothesis space can never be good, regardless of the examples we're looking at. So a good example is if we look at our background knowledge, this is like the features. If we see, for instance, we can look, there's never a number that's both even and odd. It's just a toy example, but that implies that you can never have a rule which has even and odd in. So just get rid of it from the hypothesis space. Yeah. Likewise, if you ever have a rule which says, there's a number and it's an integer and it's also even. Well, every even number is an integer. So that rule just doesn't make sense. You'd ever have, so we can get rid of it. But it was really essentially trivial for us to do this because of this symbolic representation. We could just essentially add these constraints to say, look, never generate a rule odd and even. So it's nothing. We don't have to do anything. We just tell the SAT solver.
the search just got slashed through like completely.
Precisely, yeah. Here's a constraint. Obey this constraint. So it's very easy. And this just has ridiculously powerful impact. It's taking things that I think from like 24 hours learning time to a few seconds.
Wow, that's really cool.
Yeah, because you don't have to look at the examples. You're just looking at the features, and you can do that really fast. We had these constraints. We didn't have to write much code. We add it to the solver and poof. So it's just a very nice way to innovate. Because all we're doing is just eliminating things. Like this rule cannot be true. Get rid of it.
Yeah. It totally makes sense. It's one of these ideas that's like, oh, of course. Like, why would we be searching the entire, combinatorial explosion of this search space when you don't need to,
Yeah.
But it's really interesting just ignoring the examples. That is fascinating. I guess you're hinting at it there, but where do you see, and you don't need to name a roadmap, but just bigger picture, where do you see Popper going next? It definitely sounds like you're continuing development on it.
Yeah. So we kind of got three branches. One is just really push the purely symbolic search still. Every paper we have like exponentially reduces the search space essentially. And we still have lots of ideas on how to push the SAT solvers, the ASP solvers much, much further. So that is really one thing. Let's just make symbolic search better. Another pillar, which we're looking at hopefully soon, is let's just now copy deep learning. It's just chuck loads of computers at it. Because everything, so say about the system Popper at IFP in general, it works on my laptop on one CPU and it works well.
Right. It's so efficient.
Yeah. So I sell it as, okay, a deep learning would work on a laptop on one CPU, but it would take a long time. Wouldn't really work well. This IOP works. Imagine what would happen if we had the same improvements that deep learning has through parallelization. That's quite a nice idea. It already works, so we can't be worse. We're going to be better. Yeah. How much better? So imagine we just had the same processing power. Or do we get the same improvements? That's quite exciting, I think.
It is. Now you need a funding partner or something, but yeah.
Yeah.
Because it does get expensive, but that's okay. And then that's the kind of thing we're experimenting with at India. All right, the third thing. Yeah. What's the third thing?
Oh, just neural networks, guide the search. So the whole thing about my group, my research is that we are symbolic learners. We want to learn symbolic programs. We want to do symbolic search. Because if you want to do a bit complicated, these are NP complete search problems or NP hard problems, a certain complexity of problems, use SAT solvers to do. It doesn't make sense to use something that's not that. But we could still use the intuition of a neural network to guide the search, to just give some hints. So the idea is that now we'll try to use some neural networks to just help the search along. Not to perform the search, but just to help the SAT solver. So it could even be a simple thing of, we have some data, the neural network says, I think that you probably need this relation. So this actually comes back to Dreamcoder, Kevin's work.
Yeah.
He has this thing called a recognition model, where basically you look at the examples and it says, it finds a distribution over all the functions or actions that could be in a program. We want to do the same. We're still going to use the symbolic search, but tell the symbolic solver, look, we think you should use this action. You don't have to, but we would prefer it if you did. So trying to give some intuition to the solver, break problems down, but to incorporate neural networks or some kind of statistical learning. They're the three things we're working at.
That's so exciting. I have to say, we are hiring at India. And so if these things that Andrew is saying are exciting to you, definitely apply if you've got some program synthesis experience. That sounds like our world.
Or apply to do a PhD with me.
Or apply to do a PhD. Are you looking for students? Please.
Always, yeah. And that's
amazing.
Yeah.
Oh, I mean, how if you're going into study, how could you not do this? This is definitely the coolest part of AI, in my opinion. So, and Andrew is the right person to kind of guide that.
I have friends who work on deep learning, and especially in the old times when they used to work on deep reinforcement learning. Oh, it was horrific. PhD students just couldn't really do anything. It was so superficial what they were doing. Because they would start something, they would be scooped. Then they start something else, they would be scooped. And then I just need something out there. I need just desperate to get something to get a PhD. And at least with our field, there's not many people who work at it. Maybe I'd probably even be exaggerating to say there's 100 people in the world who work on it. Really, there's even like maybe fewer, but it means you're not rushed. We can take our time, and we don't care about 1% improvement left, no interest whatsoever. We go for huge improvements.
Yeah.
So the selling point of what we work on is that you can do something that's intellectually rewarding and significant, and that you actually do something, but it's not ephemeral research. You're not going to be superseded in 3 weeks. So yeah, that's the selling point for actually doing the research. Yeah.
All right, new plan. If you're just getting into this space, go study with Andrew and then apply to India.
Yeah, good
We're
idea.
happy to see you. But this is amazing. Okay, one last question about ILP, which is in practice. So I think the paper mentions drug discovery as an example. What are some examples of ILP, actually in application, sort of real world?
I'm not sure of that many companies that use ILP, partly because I don't follow the application side so much. There's more people who do application-focused research. We don't do that. We're more just fundamental designing new algorithms, new approaches. So I can't really say, but I've read lots of papers to do with things like drug discovery where there's using ILP for case studies. So the best example I use of ILP, or the one that's the nicest, which is another work that not many people were. Have you heard of something called the robot scientist?
Oh yeah, that's a big goal in the field. Robotics is kind of taking off. So yes. Mm-hmm.
Oh, so the robot scientist was a project, or it's an ongoing project by someone called Ross King, who's now at Chalmers and Cambridge. And he essentially developed a machine that would look at some observations, would hypothesize an explanation for the observations, by their true or false. It would then actually conduct an experiment to try to refute the hypothesis, analyze the results, feed it back, and then formulate a new hypothesis, all in a nice closed loop system. And they used ILP as part of that, like to form the hypothesis, because that's what you want.
Right?
You've only got 1 or 2 examples. You need to actually execute it and see the predictions it makes. Yeah, and it was the first. This was in the 2000s, and it claims to be the first system to discover new knowledge independently of its creators. And they published it in Science or Nature. No one's heard of it.
Very cool.
It's such a beautiful piece of work.
Maybe I hadn't heard. Yeah, I don't think I had heard. I'm going to correct my statement. I hadn't heard of this particular experiment.
Yeah, because there's loads of people working on AI for science, for instance, but very few people are familiar with this. Yeah, look at it. Ross King, robot scientist, but also just exciting work.
Right? And why not both? I mean, it seems like pairing those up would actually get you some pretty exciting results too. So who knows? Maybe that will be the secret to unlocking AGI,
In terms of our work, for some reason, this seems to be really popular for people to use it for games. I'm not really sure why. So people have used it to help reinforcement learning play games by explaining like bad paths. So it's like, this path is bad. Why? So the paper I saw was when they were playing Mario, and they could learn the rules like,
that's cool.
If the bad guy is to the right of Mario or something, don't go right. So they could feed this back to reduce the sample complexity.
Exactly. Yeah. Well, it just might be a new scenario that training data alone wouldn't get you, to succeed at. And, it's almost like cuts down the search space. And so you have to do reinforcement learning on less sort of paths.
And there's Tom Silver, who was at MIT, now he's an assistant professor at Princeton. He basically used ILP to learn, he didn't call it ILP, but how to play Atari games, and just a few examples. It's really nice work, really, really nice work. Just learning, to actually get the pixel data and then learning what action to do. Really, really nice work. ILP is actually being kind of widely used, but I'm not sure it has it's still waiting for the big success, the big shiny success.
Yeah.
But, have you heard of Microsoft Flashfill before?
Flashfill, is it like a spreadsheet kind of AI tool?
Yes, exactly.
Okay.
So Flashfill is this tool where you have a column of data, and it might be, for instance, a good example would be the date formats in US format.
Okay.
And you could have and you may say, I want to translate this to a format that the rest of the world would understand. It's because no one else uses that weird format. So you have your US format, you might give one example. You might not want to write a macro. So you just give an example, you click a button, and then it learns a synthesis program. Transform that column to the other. And it makes the predictions, and you could say, I'm going to give it another example if it's incorrect. And flash fill is really good. It's really great at these string transformations. It's very popular. It had a lot of impact in academia, really on program synthesis, but also real world. I think Sumit Govani is the guy behind this. I think he said, I remember the exact number of people who use it every day, but it was in the millions.
Wow. That's amazing.
It's so frustrating because ILP could do it. They could have done it years ago, but just no one had let's do it. It's like the technical leap wasn't there.
So Flashfill is not ILP, you're saying?
It's inductive programming, but they didn't use logic as a representation language.
So it would have been way better if they had done that.
Oh yeah, much better. Yeah. No,
that's funny.
No, but just ILP, we could have done it. Like even Shapiro's work in 1981 probably could have done that, but no one just connected it. So it's a bit annoying that we're just lacking that spark of connecting the algorithms, the idea to applications.
Yeah, I predict that this will become more of a known thing, and I'm not sure how it will happen, but it's just so powerful, and it seems so related to artificial general intelligence, which is just has always been kind of the end goal of the entire AI field, right? But now is so prevalent in terms of OpenAI has their mission statement is literally about AGI, right? Or making it safe or something like that. I'm not sure what it is these days. Do you believe that this kind of bigger picture, like symbolic AI approaches will be required to create human-like artificial intelligence?
I'm not sure about human-like. I'm not really sure what it means, but I think it's needed to create better artificial intelligence, definitely. So even a simple example about the LLM, when I told it to not do something, I can't remember what it was, but it just kept giving me the same answer, and I tried every possible prompt. That's really not very smart. Let's make it clear, I'm not against LLMs or deep learning. They're amazing. I love them. That's why we want to use them to help our work. But some really stupid, annoying things like that, it's just so. So I think combining this kind of symbolic representation, symbolic learning, symbolic reasoning with neural networks, like what we said, we want to have formal symbolic reasoning guided by statistical learning. I think that's really the way to have better AI.
Couldn't agree more. Thank you so much for taking us through that, and also just doing all the hard work, 2 years of work to get this paper out the door. It's really, really beneficial to anyone who wants to check out ILP. Any parting words for folks who are, kind of intrigued by this? It caught their attention. What should they do next?
Probably just contact me or Seb, because we're the people who are trying to get more interested in it. You should get Seb on. He's much more of a communicator than me, so he's the one you should have asked
to
come on. No, ask Seb. You should get Seb on. If you're interested, just get in touch. We can write a work together. There's so many ideas. Every idea is, like I said, it has meaning. You're going to do something good if you work on ILP. It's going to be rewarding and have impact.
Yeah. Thank you so much for all that generosity and putting all this knowledge and actual application software together, or so actual software together. Would you call it Popper software? I guess it is.
Yeah.
Yeah. So thank you for putting that out there and sharing it with the world. And also, just if you do get in touch with Andrew, just don't report any bugs on Popper. He doesn't like that.
Time consuming. I didn't realize it. There's not even that many.
Right.
But yeah. If it grows, there'll be more.
It is just part of the deal, but it actually means people really care about what you're building, and someone out there is, wants to use it. So it's actually a wonderful thing, but not a fun experience usually. Well, Andrew, thank you so much for taking time today. Really appreciate it. I'll link the paper in the show notes, and people should go check it out, and they'll be able to find you from your personal website and be able to contact you there. But thank you so much for your time.
Thank you for asking good questions. It was interesting.